Okay, so question 9, same idea, but they do have a new little twist in this. Given that 1 minus 5i is a 0 of this function, find the remaining zeros and factor f of x as a product of linear factors. Okay, well, since f of x has an exponent of 3, we know there's 3 zeros. And they're telling us that 1 minus 5i is one of those zeros. Okay, well, we know from our conjugate pairs theorem that if 1 minus 5i is a 0, that its conjugate, 1 plus 5i, is also a 0. Okay, we know that they come in pairs. So there's really only one more for us to find. So I'm wondering if I can just maybe graph this and if I can tell what that last 0 is. So let's try it. X to the third minus 3x squared plus 28x minus 26. And when I graph that, my calculator here, it looks like it's touching at positive 1. Okay, so let's try and see if 1 works in synthetic division. So 1, negative 3, 28, negative 26. Let's see if we get a remainder of 0. 1 times 1 is 1, negative 3 and 1 is negative 2, 1 times negative 2 is negative 2, 28 negative 2 is 26, 1 times 26 is 26, those combine to be 0. So it does work, okay? So we know that they're telling us that 1 minus 5i is a 0, we know that its conjugate 1 plus 5i must be 0, and we just verified by our graph and trying it with synthetic division that 1 is a 0. So these are all 3 zeros with multiplicities of 1. Okay, so one of our factors, if I take my f of x, one of my zeros is 1, so that means x minus 1 is a factor. Okay, another one would be x minus the 1 minus 5i. That would be a factor. When I distribute the negative, I would get x minus 1 plus 5i. And then if 1 plus 5i is a 0, then x minus that 1 plus 5i would have to be a factor. Distribute the negative, and we would get x minus 1 minus 5i. So that is our factored form of this original polynomial function. Okay. Now I would point out, if you wanted to do synthetic division with an imaginary number, 1 minus 5i, you can. It's very ugly, it's messy, but you can do it. Okay. So I multiply 1 minus 5i times 1. Well, 1 times 1 is 1. Negative 5i times 1 is negative 5i. When I combine these, the negative 3 and positive 1 makes negative 2 minus 5i. Then I'd have to multiply 1 minus 5i times negative 2 minus 5i. It's messy. When you FOIL it all together, though, you would get negative 27 plus 5i. I'm not showing my work on FOILing that out, but I could. And then when I combine those, I would get 1 plus 5i. And when I FOIL together 1 minus 5i and 1 plus 5i, I would end up with a positive 26, which does leave my remainder of 0. Okay? It's messy to do that synthetic division with imaginary numbers, but it does work, and you could do it. But since we knew 2 of the zeros, my third one was one I could see on my calculator. I think our best bet was just to try the synthetic division with the 1 and then know that we had all 3. Okay, number 10. Given that x equals negative 1/2 is one of the solutions to this equation here, find the remaining solutions. Okay, well, this is a degree 4 polynomial, so we know there are going to be 4 zeros. And they gave us one of them. Okay, so let's graph it. Let's see if we can see the other ones. 2x to the 4th minus x to the 3rd plus 17x squared minus 9x minus 9. Okay, make sure I typed it in correctly. Sure enough, it does look like it touches x at negative 1/2, which it should, because they told us that was one of our solutions. it looks like positive 1 is another one. Okay, so I'm going to make a note here. Appears to, actually it crosses the x-axis, which means since it crosses, it's probably just each of them got used once, multiplicities of 1, at x equals negative 1/2 and x equals 1. So let's try synthetic division on those. I'm going to put a negative 1/2 in the box. I'm going to write my coefficients. I'm going to do my synthetic division. Negative 1/2 times 2 is negative 1. Negative 1 and negative 1 is negative 2. Negative 1/2 times negative 2 is positive 1. 18 times negative 1/2 is negative 9. Thanks, negative 18. Negative 18 times negative 1/2 is positive 9. It does leave a remainder of 0. We verified that negative 1/2 is a 0, which we knew. They told us it was. Now let's try with the 1. I can use my depressed polynomial here and do synthetic division with the 1. And it also gives me a remainder of 0. So that means that 2x squared plus 18 equals 0. Okay, that's my depressed polynomial. The first synthetic division got the exponent down to a 3. The second round of synthetic division got the exponent down to a 2. I can solve that equation. You can use quadratic formula, but since it's missing the b value is 0 right here, I could just solve using square roots. So minus 18, 2x squared equals negative 18. Divide by 2, x squared is negative 9. I can take the square root of both sides. Now notice when we take the square root of 9 is 3, but that's a negative 9. So that means it's going to be imaginary, okay? And remember, imaginaries come in pairs, so plus 3i and negative 3i. So my zeros are negative 1/2, which they gave us, positive 1, which we got by looking at the graph, 3i, and negative 3i. Those are our zeros. Notice they all have a multiplicity of 1. If you wanted to write this function in factored form, it would be, well, if negative 1 is a 0, then it would be 2x plus 1 as a factor. It would be x minus 1 as a factor. It would be x minus 3i and x plus 3i as our remaining factors if you wanted to write it in factored form. They didn't ask for that, but you could do it. Okay, number 11. Find a polynomial f of x with zeros of 3i and 2. And notice they said that the 2 has a multiplicity of 2. That means it gets used twice. Okay, well, if one of the zeros is 3i, that's an imaginary number. So there's going to be another one with negative 3i. Okay, and notice that 2 is our other 0. So 2 is a 0, but it's got a multiplicity of 2. That means we use it twice. So our function f of x, one of its factors will be x minus 3i. Another factor will be x plus 3i. Another factor will be x minus 2. But that one, the x minus 2, gets used twice because it had a multiplicity of 2. Some people, instead of writing it twice, would like to call it x minus 3i, x plus 3i, and x minus 2, and they would put a squared on it just to show that that x minus 2 is used twice. And that's fine. That's not a problem. Okay, number 12. Another polynomial p of x. They want it to be degree 3 with zeros negative 2i and 4. Okay, now degree 3 means there's 3 zeros. They only gave us 2 zeros. But since one of them is negative 2i, we know that its conjugate, positive 2i, would also have to be one of our zeros. So our polynomial p of x has zeros of negative 2i, positive 2i, and 4. That's 3 solutions, 3 zeros, and notice they said degree 3, so that checks out. So one of our factors will be x plus 2i, because the 0 is negative 2i, so x plus 2i is the factor. X minus 2i, because if 2i is the 0, then x minus 2i is the factor. And x minus 4, because if positive 4 is the 0, then x minus 4 is the factor. Okay? And then the last one here, what are the zeros of this function? Now notice they've given us r of x in factored form. It's already been factored for us. So the zeros are going to be positive 2. If x minus 2 is the factor, then positive 2 is the 0. Notice that it's got a squared up there. That means that 0 of 2 has a multiplicity of 2. It got used twice. Next, if x plus 3 is a factor, that means negative 3 is a 0. It has a multiplicity of 1. It did not have any other exponent. It's implied to be an exponent of 1. And then the last one will be negative 4. If x plus 4 is a factor, then negative 4 is a 0. Notice that exponent of 3. That means that its multiplicity is 3. Okay, notice if I add up those multiplicities, 2 plus 1 is 3, plus 3 more is 6. So this thing, if I FOILed it all out, would have an x to the 6th as its first term. There will be 6 zeros or 6 solutions, and that's what those multiplicities add up to. Okay, notice that because this has an exponent of 2, that this even multiplicity here, the graph, it would touch 2 and it would go back the way it came. The graph would cross at negative 3 because it has an odd multiplicity, and the graph would cross at negative 4 because it has an odd multiplicity. So that's a nice connection back to the 3.2 information that we practiced there. And you could graph it as a calculator and verify that as well.